Okay, it's 8 o'clock, so we'll make a start. So welcome everybody. Another rattling through some computational physics. So have your notebooks ready, make some jottings. Don't expect to understand all the details, but get some ideas as to what you might think about doing. Some approaches, sketching graphs, what makes the particular piece that Dr. French goes through interesting. What sort of range of things does he present? So he'll present a bit of coding and some graphs. He'll make some changes. So jot down the big ideas. Don't sort of worry about the fine detail. The project will be announced in due course, but it's not sort of looking at all of these topics or anything like that. It's a very detailed thing where you can investigate one aspect. So get some ideas from this, and make sure you've got those sort of notes to hand, so it reminds you of the sorts of things you're going to be able to present in due course. Okay, so to Dr. French, thank you.
Hello, thank you very much, Professor. Very good evening, everybody. Welcome to Waves and Optics, which is the subject of tonight's BFO Computational Challenge. If it's your first visit, hello, very welcome. I think this is number 4, possibly 5. So if you come to all of them, that's awesome. Right, so let's make a start. Waves is a brilliant topic because it kind of cuts across all of physics. So it's kind of almost a bit different from mechanics or radioactivity or something like this. So we're going to start off with the anatomy of waves. So the kind of language which we use to describe wave-like phenomenon. And then what we're going to do is we're going to do a little experiment. I'm going to have a trigger warning. I have a kazoo. So we are going to make some wave sounds. There we go. I hope you like kazoos. And we're going to analyze the sort of the wave quality of this kazoo. What does that mean? So there's a kind of key idea. If you look at the bottom, the Fourier components of a wave. So any kind of periodic disturbance, and I can think of electrical waves, I can think of sound waves, seismic waves, whatever. All right. Turns out anything that sort of repeats, you can define as a sum of cosine and sine waves of different amplitude, different phase, different frequency, wavelength, etc. So given that idea, if we can understand how, say, a sinusoidal disturbance operates and moves and relates with distance and time, then we can kind of look at all wave phenomena by just breaking them down into their Fourier components, their sines and cosines. So I think it's worth, a lot of this will be very familiar to many of you, but I think it's worth just sort of quickly going through some nomenclature. And then I'm going to show you how to plot this graph. All right, so that's going to be the first sort of bit of computation. So essentially what I like to teach to waves is that we'll get a slinky, all right, you'll wiggle a slinky, and you will get a sort of sinusoidal kind of pulse. You might have a standing wave perhaps in that to get to, you look like a real sinusoid. But essentially, you can create a sinusoid. If it's a traveling wave, a bit later, so my blue graph here is my disturbance, which I'm going to use this Greek letter for, because it could mean anything. It could be voltage, displacement, pressure, or anything you like. And that's at time t equals 0. So, so imagine I've taken a kind of photograph of this wave. And maybe think of water waves. If you're out on a cliff top and looking at some waves coming past you from the ocean, it might look a bit like this. All right, this is your blue wave. Then you take a picture a little bit later, delta t later, and if I'm traveling at speed c, that time later is going to be the distance that I travel divided by the speed. All right, so I've got a sort of a translation of my wave. So waves translate through time and space. There's a little song about that, which I probably won't play tonight, but I can show you a link to this. And there we go. So we can sort of define this as a shift. So what have I got? If you imagine, say time is 0, if we go look at the thing that's in the big red box here. So what I've got is I can map my sort of spatial disturbance with one wavelength between the peaks or between the troughs. So how many wavelengths is the number of 2 pi radians I go round? And that's how I can turn a cosine wave into a sine wave. And then what I'm doing is I'm replacing x in that with x minus ct, which is basically a shift by ct from left to right. So that's how I can construct a wave. And if we sort of multiply that out into bits, I've got 2 pi x over lambda minus 2 pi ct over lambda. And we define things called a wave number and an angular frequency, which just make that a bit easier to write out. So the wave number is the sort of spatial bit, 2 pi over lambda, and the sort of like time bit is 2 pi c over lambda. All right. And so if we're using our wave speed, that turns out to be omega t. So if you look up in a book of waves, you'll probably see the argument of your cosine, where you are in your cosine wave, to be kx minus omega t minus maybe some fixed phase that you start off. So that thing in the bracket is what we call the phase, where you are in your cosine wave. And if we can make that three-dimensional rather than just a displacement, we might have a vector. All right. And the vector might be, the position of somewhere in this wave field, right? If it's 2D, it's like where you are in the sea, etc. And the wave vector being the direction that those waves move at. And some of you may hopefully would have done it in maths. K dot r is the projection of my wave vector in the direction of r. So the k bit here, kx, turns into this. All right, that's how we can generalize a sort of one-dimensional wave into 2 dimensions, or 3 dimensions, in fact. Okay, so basically, this is a generalization of a wave. So firstly, how might you go about plotting one of these things? You could do this in Excel. I'm going to do it in a bit of MATLAB. So there's a bit busy this one, so I'm going to sort of just talk through some of these parts here, and then what we'll do is we'll sort of cut and paste it into MATLAB, and I can sort of show you. So what I want to do is create these graphs. So I've got sort of my translated, and also I've got a graph of time versus my amplitude. So the bit in the bottom hand corner here. So this is, I'm picking a certain position, and I'm saying, how does the wave vary at that point? I think the position I've chosen is probably position 0. So here we go. I've got some inputs: my weight of amplitude, my wavelength, my speed of wave. So this is going to be a sound wave. I've got my frequency and my time units here. And these little text boxes, I've got some things at the end which can use my time unit and frequency unit to actually tell me what the multiplier is. So gigahertz is 10 to the minus 9, nanoseconds 10 to the minus 9, etc. Then what I'm going to do, I could say, all right, I'm going to sort of separate my my sinusoids. So dx, and I'm going to have that as 1/8 of the wavelength, just to make it nice and sort of simple there. And then I might have the number of data points, how many waves I want to plot, and then things about the graph, for example. So the green bits are my commentary, and the other things which are not green are defining how these things operate. So I think what we'll do is we'll sort of paste that into MATLAB as we go, and I'll sort of explain as we go here. So what I'll do, here's MATLAB, and we've got a program which we're going to use a bit later. If I type the word edit, so I have a kind of command window where I can do some programming. So what I'm going to do is I'm going to sort of paste all this lot in, and we'll sort of go, actually, we'll do the first bit. All right, so these are my inputs. I think what I'll call this, I'll save this as something. So let's go for save as, and we'll call this waves. All right, not a really original file name there. I realized I've got, there we are. It's put a sort of a quote. So there we go. These are my definitions. And if I was to run this, so if I just go and save that and run, hit the green button, right in the top corner, I've got all the variables that I've defined. So let's go and do something with that. So let's copy in the next bit. All right, so what I've got here. All right, I'm going to determine the period. I'm going to get the time delay associated with my spatial separation, which I think is 1/8 of the wavelength. And then the fun bit is what I'm doing here. So what I'll do is I'll put a breakpoint at this point here, and then we'll run the code until that bit. So if I hover over these, there's my time interval. There's my period, 0.0015 seconds. There's my frequency, 680 hertz. Now I'm going to create a vector of x and t values. So linspace, we've used this quite a few times before. If I type linspace of, say, 0 to 10 in 17 parts, rather eccentrically, that will give me 17 numbers between 0 and 10 that are equally spaced. So that's a really nice way of generating data. So I'm going to do that between 0 and however many waves I want. So number of waves is 3, and that's the wavelength. So that's going to be the x extent, and I'm going to do that 1,000 points. So if I evolve that, press F10 in MATLAB, and I work my way through the code, I've now got 1,000 data points for x, 1,000 data points for t, And then I'm going to work out my my sine waves. All right, so sine of 2 pi x over lambda. So that's going to be a sine wave starting from 0. Okay, so what I've got 2 pi radians, the argument of my sine wave. And how many 2 pi's have I got? Well, it's the number of wavelengths, so x over lambda. And then the next one, I'm basically doing that, I'm shifting my x by delta x. So I'm shifting it from left to right. And then the last one, I'm just going to plot it versus time when x is 0. Okay, so I've got my sort of sine part. And if I just keep going, I think that's finished that bit. And I need to plot my graphs. So I'm going to go and paste that bit in. And that's probably going to be, I probably will need all of these. All right, so here we go. So if I go and paste in, just check I've got no errors in here. Don't think so. Right, so every programming language has its own kind of format for plotting things. So I think what we'll do is we'll go to here at a breakpoint, and then I'll step through the code and you can see what's going on. So why is it not working? There we are. Oh, there's a syntax error somewhere. Let's see if I can find it. It's somewhere here. I'm trying to find out where that is. There's some error I've got. Let's see if we can work it out. So, oh yes, because I need to make the whole thing a function, because I've got some functions here, things which do stuff. So I've got to start off with making this a function. So there we are. So function. And we'll call this waves, I think. There we are. All right, so that basically means everything that happens in here, I won't expose to the command window unless I ask it to. Right, here we go. So I've cleared everything. Let's go down to this point, so line 33, and let's run it. Here we go. So everything's now displayed because we're kind of in this function, and I'm going to step through this. So I'm making a figure, and then what I'm going to do, I'm going to plot x versus yx1. Remember that's the blue curve, and x yx2, and that's going to be a red line with a line width that I've defined, which is 2 units. So that's all you need to plot this graph, is to create a figure. In fact, in MATLAB, you don't even need to create a figure. You just have nothing there. The plot command is all you need. But that's not a very pretty graph. It's got no axes, etc. So I'm going to add a legend, and that little bit of voodoo here, slash delta t, this uses latex. So LaTeX rather, not latex, not the rubbery stuff. And that gives me some Greek letters. If I just keep going, oops, when my graph has disappeared, there we go. Oops, I need to keep my graph on there, and then, right, it's got silly. Right, if I just move this across, there we go. Hopefully that will remain. Right, I might have to sort of minimize this so you can see the graph evolving. There you go. Right, so here's my graph. So if I keep going, right, so I've made a title now. There you go. There's my title. Always a good idea to have a title in your graph to explaining what's going on. So this is probably the most complicated bit of coding I've got in this little program. So I've got a title, and I've got this sort of thing in square brackets. So in MATLAB, everything is a matrix. And so what you've got, matrices are things with square brackets. A bit easier in Python, but I suppose it's straightforward in the sense that everything's the same. So I've got A equals, and then I'm converting the numerical value of my amplitude into a string. So things in quotes are strings of text. And I've got converting the wavelength and the speed of sound as well. So this is really useful because I can then put calculations in my title, and the graph I'm going to produce will contain those things. That's a really nice little thing to do. So when you create a graph, everything should be there. All right, if I keep going, I'm going to set the font size to be a decent one. I'm going to make the axes tight to the graph, and then I'm going to print it to a PNG file, and then I'm going to go and close it. All right, and then I will do the other one as well. So I'm plotting the time. There we go. So this is how I can make a really nice looking graph. All done. And if I open up the folder, hopefully it should actually have my my PNG files. Oops, not new folder. Oops. Show in Explorer. And there you go. These are my files. So I'm going to get rid of that. And I've got wave y versus x, which is really high quality. Something I can stick into a document. And I've got the time variation as well. So everything is all defined. So learning how to plot decent graphs, ladies and gentlemen, is a very good idea. Right. Okay, so that is the kind of basics of waves, where you are in a cosine wave. And we've got things like wave speed and period and wave number, etc. But that's the key idea. Right. Can I just double check that I'm coming across okay still? Any questions that have arisen so far?
Yeah, all good. It's pretty quiet with the questions.
Fantastic. Right. Good stuff. Okay, so what we'll do is we'll have a little look at standing waves and how you might see them. So here's an app that I wrote a few years ago, which is how you can represent a standing wave. Now remember, say the green one here, we've got a standing wave. That's at one point in time is the green wave, you see. And when you see this in textbooks, you'll see these sort of like little different colors. It's a bit like, you know, when you plucked a guitar string. So what you really need is something dynamic. So in the computational challenge, a lot of the sort of gold entries, and in fact the ones that have ended up winning, have ended up making apps. And this is, you know, not just a graph, but a graph with sort of human controls, if you like. Particularly ones some people have made phone apps as well, which you can use gestures and all that stuff. So I'm going to show you an app. The downside, of course, it's a lot more complicated to construct than just a sort of simple plot command, etc. But you know, this is where you can go with these things. So these are all my apps, which you can download from the Eclecticon. We're going to have a little look at what's it called? It's called Standing Waves. There we go. I've got a very you know, sort of is what it is kind of title. Right, let's go for get rid of all of these. Okay. Right, so here's my little app of standing waves. Let's minimize all of this. Okay, so here we go. Actually, I'll put my put the presentation back in the background so we don't have any distractions. So what we've got, this is a 340 hertz wave. Wavelength is 1 meter. This is the period of the wave, not very much. This is the wave number, 2 pi of the wavelength, and this is my angular frequency, 2 pi times the frequency. And so what I've got is a screenshot of this wave, a sort of snapshot, a photograph. And what I can do is I can evolve it in time. And so if this is a standing wave, oops, something's not happening here, bear with me. I might just run that again if that's all right. Yeah, there we go. Right, let's just run that again. There we are. Right, so hopefully that should work. Good. So my standing wave, so as I evolve time, you can see what's happening to the wave. All right, so this is not the fundamental, it's the first harmonic. So I've got a node in the middle. In fact, let's have the first harmonic, the fundamental wave. Right, so if I've got a guitar string, I've got a node at both ends. That's what constrains it. And in fact, I'm teaching quantum mechanics at the moment to my 4th years. And the quantum in quantum mechanics is because things are discrete. Electron waves around a hydrogen atom, that's the Bohr model. Yeah, you've got 2 pi r, the radius, the circumference of your circle, is a whole number of wavelengths. That's the standing wave idea, which prevents your electrons radiating and your electrons spiraling into atoms in about 10 to the minus 11 seconds and making sure we can exist. So the quantization, the quantum bit, is something that is true with all kind of standing waves. We've got a constraint. So guitar string, we're not allowed to move at the end of each string. And if you can see my picture, here's guitar. So there we are. Here's a guitar, and we've got a node here, and we've got another node at the other end here. All right. So don't know if that came across. So what we've got, just going to drop my guitar. Little place. There we go. Right. So we can have extra harmonics where we can have extra nodes. That's the first one. That's the second one, etc. And if your physics teacher is suitably mean, they'll make you kind of sketch these. What I would recommend doing is doing the nodes first and then kind of drawing the waves in between. Otherwise, you end up having your periods being all sorts of strange distances. But anyway, the idea is your wave evolves with time like this. And so what I've done is I've superimposed different times, and hence we get the extra waves in between. Okay, so the sort of dynamic of this is important. Now, alternatively, we could have a different viewpoints, and I've got 3. I've got the red one, the black one, and the blue one. And this is at certain positions in the wave and how they evolve with time. Okay, so you can see the red one is just off the antinode here, so it's quite large, whereas the black one is closer to the node. So if I move the position of the black one, you can see the amplitude changes, but those are all in phase because they have the same time variation. But what is different is their amplitude varies as you go along the wave. And those are the kind of A-level questions that you often get. All right, so there we go. I can also have a very fun thing if we have, let's just say, an organ pipe. All right, so there'll be a nice little thing. So can you tell me, you write in the chat, what's the quantization condition for an organ pipe that's driven at one end and is open to the atmosphere at the other? What constrains the wavelength? Go on, tap that into the chat as fast as you can.
We're getting width, length, diameter.
Right, interesting. Okay, so if we say on a guitar string that the length of the guitar, all right, between the two nodes is a whole number of half wavelengths. So we can see that if I go for harmonic number one. So they're fundamental. So that's half a wave. All right, so the length of my string is half a wave. For a second harmonic, the length of my string is 2/2 a wave, so my wavelength. If it's harmonic number of 3, right, I've got nodes at all ends, so I've got 3 half wavelengths, so a whole number of half wavelengths. So what's that got to be for an open-ended tube? Or I've got a node at one end and an antinode at the other. Oh, we've got all sorts of interesting things coming here now. So I've got some quarter wavelengths. What's popular, Nina? Oh, there we go. Right. So TJ131, congratulations. So it's an odd number of quarter wavelengths. It can't be an even one because that means we might have ended up with a node at both ends, you see. So if we click on this button here, which says nodes at both ends, and turn it off. So the way I've specified it is I'm going to have a node at the right end and an antinode at the other end. And that's fixed. So if I go back to this one, the simplest one is that's now a quarter of a wavelength. If I go up to a next harmonic, all right, I've got an antinode, a node, an antinode, and a node. All right, so that's 3/4 of a wavelength. Next one is going to be 5/4 of wavelength, and you get the idea. All right, so there we are. Here's my X is now right at an antinode, so I've got nothing. If I make that a bit bigger, you can see the amplitude growing, but it's still in phase. All right, so it still has the same time variation, but the sort of envelope of that will change. So there we go. I hope that's giving you some food for thought. So what are the key points here? Well, firstly, let's go back to our presentation. We can sketch a wave, and we can look at wave at different times. Where's my presentation? Here we go. There we go. And we can use some presentation tools, but ultimately you've got a wave translating. And then we've got the idea, maybe you can put that into an app and you can see how things vary dynamically to kind of get a sense of what's going on. So there we go. That's an open-ended tube. And if you want to be really, really sort of like accurate about this, what you find is that you get a kind of end correction. So the tube is actually as if it was slightly longer. So the node of pressure, so when you have an organ pipe, you sort of drive it to the high pressure end here, and the other end is connected to the atmosphere. So that's going to be an atmospheric pressure. But actually what you find is the node is a bit beyond the pipe. And it's intriguingly about 2/3 of the radius of the pipe beyond it. All right, so there we go. And that's an odd number of quarter wavelengths. So there we go. That's a little idea. Right, so we're going to do an experiment now. So this is a sound analyzer. And I think I said it earlier that we can have all waves are a Fourier sum, so sine and cosines of different frequencies. So I think this is physics is the best subject. I don't know if I can play this. No, I don't think it will work, that one. No, so I'm going to go and record something for you. So there we are. If we get rid of this little app, and you can get all sorts of these things, like Audacity is very good, but this is a few years ago. I thought I'd write my own sound recording and analysis app. So what you can do is you can upload an MP3, but it's a bit more fun to record it. So I'm going to do, I'll go for a high frequency, a middle frequency, and then a low frequency in about 5 seconds. So let's see what happens. I was a bit noisy for the first one, so I think I'll try that again. There we are. we go. I've got a sort of a rock kazoo here, it seems. So what is this graph looking at? Well, I've only got 10,000 hertz being the main axis. I think what I'm going to do is I'm going to set that to 3,000 hertz. You can see what's going on. It's still a little bit on the noisy side here. I don't know if I can get a pure tone. That's better. Go on, let's do one more go. Or I'll just sing it. Perfect. There we go. Well, not perfect, obviously. So what we've got is something which is almost an A, just below 400 hertz, and then double that frequency. That's the first harmonic, triple, etc. And then it gets a bit noisier. And what you can see is frequency versus time on this graph. So what I'm doing is I'm sampling for 100 milliseconds, and I'm doing something called a Fourier transform. What does that do? It basically says what are the amplitudes of the sine and cosine components which make up my wave. And I'm going to plot that in a sort of column here with different colors. So red means the sort of largest energies, so amplitude squared, and the other colors mean not much at all. When you've got a kind of red line all the way, that means I've got sort of broadband noise, so sort of you can hear. So if we zoom in on the actual waveform, red is left and blue is right channels, I think. So if we go to say at 1 second, T min and maybe T max will be 1.01, what you can actually see is the waveform itself. All right, so you can see some repetitions here, but it's also quite noisy. If I maybe go to maybe a bit beyond that, so 1.2 seconds maybe that's a bit less noisy. 2, 1, something like that. Oh, let's go for we'll go for 1.2 seconds, and we'll go for maybe 1.22. There we go. So we can see that sort of frequency, but there's quite a lot of noise in it. So much of analysis of sound, of electromagnetic rays is all about looking at repeatable signals and what frequencies are in it. And this sort of spectrogram is a great way of analyzing these, because you can see how the frequency content changes with time. And we've not just got a sine wave, we've got all those harmonics as well. And I think if we go up to 5,000 hertz, you can sort of see that actually that sort of starts to get a bit muddy. But we've got loads of harmonics here. Now the key thing, I guess, is that as you're going from the 3 notes, all right, we can see the sort of the frequency, the fundamental frequency, getting lower and lower, and obviously our difference between our harmonics is getting smaller and smaller as well. There we go. So that's a nice sort of fun thing to do. Cool. All right. So this sort of spectrograph allows us to analyze all sorts of things. So I think this is physics is the best subject or something like this. And the signal power is presented in decibels, which is 10 log to the base 10 of the signal power. And you'll find that in all sorts of applications. Right. Okay. So a little bit of music first. So here we go. Music's been around for a long time, and Pythagoras, 2,500 years ago, the Pythagoreans thought that sort of harmonious intervals were things like 3 to 2, so frequency ratios of, say, 3 parts to 2. That's what we call a fifth, by the way, which is sort of in rock music. And what we can call an octave is when the frequency ratio doubles, rather the frequency doubles. So, for example, if you play an A, which typically you define as 440 hertz, 880 hertz is the next harmonic, double that. All right. Whereas the octave below is 220 hertz. So although this isn't quite like Pythagoreans did it, what you can do is you can do it geometrically. So every note going from, say, an A to a B flat to a B to a C, etc., you're multiplying by the 12th root of 2. So there are sort of 12 steps. So over those 12 steps, you end up multiplying by 2. And that's very, very close to these nice ratios. I think I might have a little picture of that. Even better, though, I have a picture of my partner, Lucinda, who's a musician. So she's playing a concert A on the violin. And this is my spectrograph. And what you can see is that because she's bowing the music constantly, then you don't have any diminution of the frequencies. It carries on. You got a really pure frequency at 440 hertz, but we've also got loads of harmonics. And some of them are louder than others. That's kind of characteristic of how your violin works. If you actually zoom in on the signal, you can see these are repeating, well, 440 times a second. So 1 over that is going to be roughly the time between these peaks. But you've also got lots of other little peaks which correspond to these higher frequencies. All right, so using a spectrograph allows us to kind of look at all the different frequencies of cosines, of sine and cosines that make up a signal. So that's the violin at 440 hertz. What does another note sound like? Well, this is a guitar, and it's quite different. So I think I'd be naughty not quite use the same time scale, so naughty me, but they are the same based frequency. But what you can see for a guitar is when you pluck a string, the string sort of the higher frequencies fade over time. They're wiggling against and pushing against the air. So you end up with a kind of bass note, and the higher harmonics sort of disappear after about a second or two. All right, so that's quite a different sort of like a plucking percussive effect. And then if you have a flute, for example, just like a violin, we're continuously pushing into energy into this. But you see a much sort of smoother range of harmonics. All right, so you don't get the really high ones for the violin. And the wave shape itself looks much smoother than the violin does. It actually has all these higher harmonics. So the kind of a sound of a flute is different from that of a violin, even if you're playing the same note. So there we go. This is a chromatic scale. So I've done do 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 do, that kind of thing of a piano 2 octaves, and you can see the signal here that I'm playing. So you have a sort of exponential decay of my signal because I'm hitting a note, and then that's diminishing with time. And there's the left and the right channels, and you can see the sort of gaps of these, the harmonics as they go up. You get some nice sort of curves of the harmonics. All right, it's a power law. Okay, so so there we go. So that's a bit of music theory, and we can analyze this with this sort of thing. Okay, so before we move on to another bit, do we have any questions about anything we've met so far?
All good.
Excellent. So there they are, plotting graphs using some mathematical models, for example, of frequency versus, where you are. So going from, you could type a note. What does that look like on a graph? That'd be a really nice thing to do. Here we go. So here we are. It's a lovely photograph that one of my students took a few years ago. So these are 2 gratings. So there will be sort of, I think it's about 100, 300 or 600 lines per millimeter. So 1 millimeter divided by that number is going to be the sort of gap between little sort of small sort of apertures within a sort of a piece of plastic. And so what you're doing, you're getting constructive interference of the lasers between those gaps. And what you find if you have, say, a green laser versus a red one, you'll get this sort of pattern of diffracted rays that come out of my grating. And you can sort of see the difference between the red and the green ones here. So this is a sort of classic experiment you'll do in the 4th year. And you can make it really good by having a smoke machine. It's a bit of glycerol in the air, so you can actually see the beams rather than just the spots on the wall. So bit of maths, and then we're going to do a little simulation. So basically the idea is you've got some plane waves here, and you've got some very thin slits. All right, now you can model this with thick slits, but there's a sort of simple thing you'll do where this is much, much smaller than a wavelength. And the idea, if you're a long way away from your slits, in my grating, D would be the distance between my slits. That will be, it was 100 lines per millimeter. That would be 1 millimeter divided by 100. Okay. And what you say is that if a long way away, so many wavelengths away from this and many slit spacings, you can imagine the waves that kind of emanate from those points are plane waves. So in fact, this is the approximation that R is bigger than D squared over lambda, actually. And what you find is that d sine theta is the path difference between those two. So the waves have to travel a bit further from the bottom slit compared to the top one. Now, if d sine theta is a whole number of wavelengths, then you get constructive interference. So d sine theta is n lambda, or sine theta is n lambda over d. And so if you inverse sine that, which is, you can kind of scrub out the sine if it's in radians and theta is small, you'll get peaks in a graph, which looks a bit like this. So here's another little app which kind of visualizes this, but there's some other effects too, which to see if you can spot. So let's go and run the app. Let's get rid of the old one. So let's have a look. It's called Diffractor. There you go. Right, so, okay, this is called the Fraunhofer far field diffraction pattern. named after Mr. Fraunhofer. It basically means you are a large number of wavelengths beyond the pattern itself. So let's go and let's go for a double slit, shall we? That's a Young's double slit. There we are. And let's have the slit width to be really, really tiny, like so. So what we do is we have a pattern here, and the peaks are when d sine theta is n lambda. So, or I think I'll use S here. So S is the slit width. So at the moment, the slit width is 3 wavelengths. So what I've got 3 wavelengths times the sine of the angle is a whole number of wavelengths. So in other words, the sine of the angle is a whole number of wavelengths, whole number divided by 3. And so if you work that out, inverse sine of a third is about 19 and a bit degrees. Inverse sine of 2/3 is that one, and inverse sine of 3/3 is 90 degrees. So those are going to be my peaks. If I increase the slit spacing, right, you can see what happens, and my my peaks now get a bit closer together. All right, so D is now bigger. All right, so I can have more angles that satisfy D sine theta equals n lambda, or sorry, S sine theta is n lambda. So if I go to 7, for example, I should have 7 possible ones from 0. So 0, 1, 2, 3, 4, 5, 6, 7. There you go. All right. So as the slit spacing gets larger, the kind of beam, if you're struggling to sort of comprehend what this means in terms of the previous, if I go back to my slides here, here we go. Right. So the angle that I've got theta is the angle from boresight. So the really strong green one is 0 degrees, and I track angles as I go out. So this particular one I've got n equals 0, 1, 2, 3, 4, 5, maybe 6 if you're lucky, something like that. Okay, and the red one, it's harder to tell. So there we go. Now, I wonder if you can sort of see what happens when I actually increase my slit width. Or in fact, let's do the number of slits first. So this is a double slit. If I have a grating, what happens is it gets much sharper. So if I expose more slits with my laser beam, remember if it's 100 lines per millimeter, you might expose maybe 100 slits. What we get is really, really sharply defined points. So there we go. Oops, that's just one slit. And if I have my slit width increases, what that does is it puts an envelope on this and depresses the larger angle ones. And eventually we get to a single slit pattern itself, which has its own maxima and minima. So for my slit width is, say, let's go for 2 wavelengths. All right, I've actually got a peak and a trough. I've got some zeros. And it turns out, if you work this through, that the slit width times the sine of the angle is also a whole number of wavelengths, but that's for the zeros, excluding the central one. So that makes for a really interesting problem when you combine all those together. Okay, so that's another example of an app which only does this thing and allows you with some little bars here to explore different regimes. And that's something which, you know, I certainly recommend once the challenge is released. All right, okay, so let's go back and have a little look at something else. So here we go. Let's go back here. All right, so we've done this one. There we go. So I won't go into this too much, but there is actually a formula behind this. So if you were, I don't think this is the challenge this year, but if it were, then I would give you this as a recipe, and then you can code up this formula, maybe look at the notes where it comes from, and then you could actually, that's what underpins the graph I've just shown you. So you can vary n, the number of slits, s, the slit spacing, and w, the slit width, and then you can plot this graph, and all the things will dance before your eyes. So this in general is a really powerful idea that once you've got a physics formula, go and plot it in a dynamic way, and that will allow you to explore all the different regimes that your equation occupies. Right, I think I'm not going to get into that. So here's a nice little idea. So we're going to go back to sort of optics now. And one of the first laws of physics in optics you'll probably learn is that of reflection. And everyone knows, I think, that the angle of incidence is equal to the angle of reflection. All right, excellent. So have you ever wondered where that comes from and how you might prove it? So it all goes back to a more general principle, which is quite strange. And the idea is to minimize the time it takes from a ray to get from A to B, such that it bounces off the surface, of course. So let's just imagine that the law of reflection doesn't quite work. So these angles are different. And what we're going to do, we're going to go from A to S to B. All right, and these are, so what we would like to know is that if I work out the time it takes to get from A to S to B, and I kind of vary that with maybe this position, so I can move that point along here. Now this isn't a dynamic simulation, but it could be. And you could have a little button which moves this point here and finds out how long it takes to get from A to S to B. You will find that the minimum amount of time occurs when theta is equal to phi. So the maths of this is really lovely as well. So you work out the time with some Pythagoras' theorem. So x squared plus y squared is square rooted is the distance, and you divide that by the speed. And I'm using c over n because I might have a refractive index in this. Obviously, it's irrelevant in this situation, but when we look at Snell's law of refraction, using a similar idea, that's going to be important. So this one, I've got L minus x, right? Squared is the bottom of that triangle. Y here is the top of the triangle. So I can use Pythagoras to work out the time it takes to go from S to B. And so what I can do is I've got it in terms of x, and I can differentiate it. So if you've not done any calculus, don't worry about it too much. But for those who have, I can differentiate these with respect to x. And I can basically ignore y. I'm assuming y is a constant. And if you do that, you get this little expression in the brackets. Now, what you can do is you can use some trigonometry. So x is y tan theta. So we'll look at that triangle carefully. And L minus x is big Y tan phi, which is, that's interesting. What's big Y here? I think that should be I think that's a mistake. That should be a little y. And if you plug those in, what you end up with some trig identities, you find out that the rate of change of time with distance goes as the refractive index over the speed times a difference in the signs. And of course, the smallest that can be, you know, if you plot a curve of time versus distance, which is this one, right? So that's basically that thing in the red box I'm plotting here versus x. The bottom of that curve is when theta equals phi. All right, so when it's equal, or alternatively, x is L over 2, and then you get the same idea, which is rather nice. So this sort of idea of it's called Fermat's principle of minimum travel time. It's just a really nice thing to actually plot. That's a complicated looking expression, but you know, finding the minimum of it gives you something quite revealing. So if that was fun, you can do the same thing for refraction, which is this. So it's a little bit more complicated, but it's the same kind of idea basically. Ah, yes, that's why I've got the big Y here, because so refraction, you're starting from A and you're going to end up at B. And so what you're saying is, all right, I've got to go from A to S to B, parameterized by my distance here. All right, how long does that take? We've got to be a bit careful because the speed of light or speed of waves, it's going to be light, isn't it? Because it's a refractive index. The speed of light in this top one will be c over n1, and the speed of light in the bottom one will be c over n2. So we've got to be a little bit careful here. And then we do the same thing. We plot the graph, all right, of time versus x, all right? And then you can do some calculus, you can differentiate it. And if you do that, you end up proving Snell's law, which is n1 sine theta, or n1 sine theta 1, as it were, is n2 sine phi. So that's just a really nice thing to do. It's like a result that you see quoted at school, but it's quite cool to prove it and to plot it from more sort of fundamental things of minimizing the travel time to this point. All right, and I've got the sort of the final version here, which is Snell's law. There we go. Hope that's fun. Any questions on that kind of thing? Any in the chat?
No, nothing so far.
Excellent. So there we go. So that's something that you all know, but you could perhaps look at in a slightly different way. Right. So here we go. This is going to be a series of simulations of ray optics. I think the best thing to do really is just to sort of show you these. So what we've got is, I'll go and move the app. So there's a very, very good one called Geometric Optics from PHET, which is excellent. But I did make these a bit before then. And I can upload more pictures. So it is under the physics one. So this requires something a bit different, that not only are you plotting a series of points, but you can also import a bitmap, which is basically a sort of grid of points and then assigning colors to it. So it's under code, it's under physics, it's under optics, and where is it? Lenses. There we go. Right. So we'll go for a converging thin lens. All right. Let's have Sybil the cat. Fortunately, Sybil isn't alive anymore, but Sybil's been replaced by Rosie, who looks very similar. So what we've got, what's going on here? Well, we've got a very distorted cat, but this is the source of the light. So imagine this is a sort of light bouncing off the cat, right, and radiating in all directions. And it happens that some of that light goes through a lens. So this is a biconvex lens. So what I've done is I made a little program. I've drawn some sections of circles, and what I've worked out is I've applied the laws of the lens. So if the light goes through the center, nothing happens. But if it goes horizontally, it goes through the focus of the lens. So obviously real lenses don't quite work this way, but that allows you to work out where that spot ends up. Now, you've probably done this with a ruler many times at school, but you can actually do it mathematically, all right? And I think, the equation is 1 over u, which is that distance, plus 1 over v, that distance, is 1 over f, which is that distance. And that gives you an expression for y versus x, which means any spot on here can be transformed to a spot where my image is. So we might project on a screen. And you can sort of see that you get a bit of distortion in terms of magnification when you're a bit kind of close to your lens. So we get an inverted image, but I can work out what happens to the cat. So there we go. That's quite fun. So the key bit here is I've also got some, I'm using my arrow keys to move the spot around, and then my image will update automatically. All right, so how you are importing an image, every language will also have a different one. That gives you a sort of a grid of data points, and you can transform those using our lens. So what's the maths of this? It's very simple, actually. It's this. All right, so if you look carefully at the bottom formula, you've got 1 over x is 1 over plus 1 over little x is 1 over f. So that's xy, that's big xy. And then you can just use the idea of that sort of straight line that goes between the two to convert y to little x. You can kind of use similar triangles or something like that. But basically, that's the expression I've got for this. That big Y here is big X, all right, with a minus sign, and the ratio of Y to X is the same as little y to little x, because they go through the origin. So you can do a few others like this. Oh yeah, that's the maths of it, but we need to look at this. If you have a magnifying glass, so in other words, that's within the focal range, that's now a virtual image. I want to see this one. So if I quit this one and go to a magnifying glass, loading for time. There we are. So let's go for James Clerk Maxwell for the moment. Here we go. Here's James Clerk Maxwell, and now he's in the within the focal range. We've got the same kind of transformation, except obviously this is now within here. These are our diverging rays, our observers over to the bottom left, and our eyes are seeing these diverging rays and asking ourselves, where are they coming from? Well, if we extrapolate those lines backwards, they'll come from here. So looking at a lens, we see that as a magnifying glass. And this is, of course, the virtual image. Maxwell's beard looks enormous at this point. Now, that's all good fun, but what happens if we have a curved concave mirror? That's going to be interesting. And mirrors are slightly different from lenses. Let's have a little look. What you get is this, all right? So the analysis of this is a little bit trickier, but this is, I think, the best example. So what's going on is that instead of refraction, we have reflection. And so if we follow a line here from one spot on the top of Maxwell's forehead, all right, it will bounce off the mirror here. This is a concave mirror, a spherical one. We've got a searchlight, one of these in my school, which I think dates back to the Second World War. And this is the normal. And that angle is going to be the same as this one because of the law of reflection that we met earlier. So the rays from here are going to end up somewhere on this line. But also, if we go straight through the middle of the circle, we're on a radial. So the rays will bounce off this point and end up. So in other words, the image of the spot on Maxwell's head will be somewhere along this line and somewhere along this line here. So where they cross, and you can figure that out mathematically, is where this green spot is. But what's really brilliant is, of course, that's a real image. That's a source of light. So I have an experiment in fact, it's in my lab right now. So if any of my students here, hello. This is it. It's a flying dinosaur now. Well, it used to be a flying cow. We're not quite sure what happened to the cow. I think it might have gone to glory, as my gran used to say. But this is a sort of a section of a spherical mirror. and you hang the cow or the dinosaur upside down, and it doesn't really do it justice, but when you go about a meter or two away, the dinosaur appears to be there sort of hanging in space. If you give it a little push, it kind of comes towards you and looms. It's quite extraordinary. People try to swipe the dinosaur, but of course it's it's nothing's there apart from light. So so I think we had this sort of final simulation or thereabouts. So where we got we've got mirrors. If I go for a concave mirror, all right, so here we go. And oops, I'll just try to run the program in itself. Let's go for the dinosaur. Here we go. So there we are. Here's my dinosaur, and that's what it will look like now. So if I move my dinosaur away, you can kind of see what's going on. There we are. That's my dinosaur. So you get some massive distortion, couldn't it? There we are. So that's an extreme, how we can use geometry, but also mapping of coordinates. So the XY coordinates of this image all get mapped to an image coordinate here using what's happening to the red to the green. But of course, you can imagine a whole grid of red spots going to a whole grid of spots over here. Right, so we've got a few minutes left. What else have I got? Let's have a little look. There we are. So you can do a convex mirror, and that's a sort of maths involved, but you get it's the same kind of idea, slightly different mapping. I'm going to skip over that, but this one is a really nice thing to do. So I saw this demonstration, in fact, with Professor Chung a few years ago. We went to the Science Museum, and if you go upstairs to where the maths exhibit is, you'll see this. I don't know if I have a picture of it. I don't have a picture of it, I'm afraid. But basically, it's a kind of old style medieval sort of ship with guns and sails and that kind of thing. And it's painted on oils and it's incredibly distorted. And what you do is you place this sort of polished cylinder of metal in the middle of the image. And if you look at it, you see the ship in this sort of full 3D glory. So this is called an anamorphic transformation, an anamorphic image, and you can make these yourself. This is one I did with CybilCAD. And what you can do is if you have a kind of tablet computer, which you can zoom in and out, all you need is a bit of kitchen pole. That's what it is. Which I went to the DT department and cut it for me, make sure it's not too sharp. And so what you do is you stick it in the middle of your screen. So you create a circle, a unit circle, and you stick the image inside it. So that's a bit of thing you can do in software. And then what you do is the sort of X coordinates are mapped to polar angles. So I think this diagram probably explains it better. So here we go. Here's my picture of Sybil, and I map her to a unit circle. There we go. You can see it's a unit circle. And then what I do is the sort of pixels in the width here get turned into angles over a certain arc. So if I set my arc to be, say, 160 degrees, all right, that's going to be, 0 to 80 degrees either side. All right, and so basically I imagine a kind of radial grid, which I transform the grid of this to. But importantly, I also shift it as well. So the origin here is down here, okay, not right in the center of the image. That's quite important. That's how you do it. And you can have a sort of scaling factor as well. So rather than 1, that could be a factor of 3. And you better play around with these two parameters. But that gives it a good approximation of what we call an anamorphic transformation. It's a bit like really looking at an image in a concave mirror, concave cylindrical mirror. So there we go. You can give that a go yourself. You can kind of see if you can figure out that transformation, and you can make yourself a sort of 3-dimensional version of any image you like. Here we go. So here's me. So this is at Fear and Loathing in Portmeirion. You've been to Portmeirion in Wales, you'll know what I'm talking about. There we go. So this is sort of a very distorted version of my face, but you can get a sort of 3-dimensional version if you place it in that little circle. So there we are. And I think that's probably all I want to talk about tonight. There's a few other bits and bobs, but I think that will be for another day. There's some things on the Doppler shift, but I think we can do that a bit later. So there we go. Hope that wasn't too sort of freaky to see a distortion image of me. Let's go for a cat instead. That's much better. Thank you very much, everybody. Unless we have any further questions. Any further questions? Nope. Fantastic. Well, good luck. And we'll see you next week for some more physics, for more computational stuff. But yeah, try out some of these ideas.
We're not here next week, Andy. It's half term.
Oh, yes, we are. So it'll be 2 weeks' time. Yes. Have a great half term.